crystallographic and orientation. Position tentatively determined, price determination will require polishing of the cut edges. The crystal cutting technique are critical, so it is very important that you need to cut the crystal very nicely, because it will require saw and then polish it and so on, because this actually tells us that the effect can be produced. The crystal's growth on 001 phase, in its phase was uniform compared to the growth on 1G. The dielectric loss on the IML-1 crystal was significantly lower than the crystal grown on 1G and lower in this phase time. The infrared detector, G star was compared with 1G and its phase time 3 and other crystals, and we found that it was almost 2 times better. The local acceptance angle for diffraction for uncut crystal was accurate to 1 to 2.5 seconds, indicates extraordinary crystal regularity. The incorporation of the metal ion impurities of the crystal found to be favored in space compared to the ground. And this is interesting. If you dope a crystal with a dopant, like if I want to put iron in the TGS solution, the dopant uniformity is much better in space. The reason is this, that when you put a dopant in a solution on a ground, like iron sulfate, the iron sulfate try to move towards the, because the gravity goes away from the sheet crystal. So the incorporation of the impurity of the dopant into the crystal is not favored. But if I put a dopant in a solution in a space, the dopant stays where it is. So the incorporation of the dopant is much uniform in the space-bound crystal. That is why I say this, that incorporation of the metal ion impurities is found to be favored in the space experiment. The reason is this, although we did not dope the crystal, but the cell of the TGS for the flight was made out of copper, which was completely gold plated. It was gold plated to avoid any effects of the iron, because TGS is slightly acidic. It has a pH of about 1.7. So, but it turns out that when we got the flight seat at the Edwards Air Force Base in California, we went to pick up the cell there. So as soon as the cell came out of the instrument, I look at the crystal. The grown crystal was covered by that cap. I could see it. But there were more crystals which got crystallized because of the lowering of the temperature, because the cell was sitting in the, I think, at the Air Force Base, so the solution became more supersaturated. And when I saw that, I saw some crystals grown at the bottom of the cell. And some of them were elongated needles, some of them were polyhedral, and some of others were different shapes. Then I immediately realized that there is some problem in the whole cell. Copper gold coating was not very uniform. And some places it peeled off and the TGS acidic solution attracted. So the crystal, we knew from the lab, we are all prepared. We had grown doped crystals in our lab. Downstairs, if you see, I will show you that the iron doping makes the crystal elongated. Nickel doping makes them different. So we had a pretty good picture of the dopant effect in the TGS crystal. So as soon as I saw, all the NASA guys were there, astronauts were there, and I said, oh, looks like the cell does not behave very well because it has some doped crystals at the bottom of it, which was not my crystals, randomly grown. They said, how do you know? I said, we know because we have done crystal growth of dopants with TGS. So we took those crystals out and measured their properties. We did an optical absorption technique to measure what their content was. And we were right. Some of them were iron doped, some of them were, but although their dopant level was very low, but it's still there. So, in the space, if I really want to do an experiment with the doped crystals, NASA has now stopped flying shuttles, so we don't have any experiment unless we go to the space station. So, it will be a very good, interesting experiment to do. Doping can be very uniform in space. So, if I want to dope crystals, that's why they were doing silicon. They didn't bother to grow ever because it's grown at a very high temperature. We did very vortices which can go up to 1,000 degrees Celsius or more. And silicon has been perfected very good. They tried mercury cadmium telluride in space, which is a ion detector material, and that they tried a couple of times. Because that also requires high temperature, but it can be done. As I said, the material figure of merit of the IML crystals were better than 1G. We have mapped the particle motion for the particle sizes. We observed and quantified the initial random walk in the IML mission. We measured the residual acceleration level in the space shuttle. It was measured first time, that was an order of over 3 times 10 to the minus 6 G, and so on. These are the various crystals which I was mentioning. You see here, this is a one kind of doping. It makes the crystal elongated. This is an undoped crystal here. It is multifaceted. And when you dope this, different phases grow at different rates. The reason crystal, like for example, if you take this crystal which is undoped, and if this is a phase here somewhere 0, 1, 0, which is the fastest growing phase, this phase eventually grows out and becomes a point, because it grows that way. So various dopants actually changes the surface energy of phases, and the surface energy is the one which determines the growth rate. So in this case, it grows in this direction more, and this is another crystal, it grows a different way. So these are all various iron dope, nickel dope, and so on. So we prepared all this in advance, and this is a picture where I just want to. This is Dr. Agarwal mounting the flight seat, which you have seen before. This is in a control room at NASA. Before the flight, myself and Dr. Roger Cruz, a NASA scientist, they were actually examining the chamber. Before the flight, Dr. Agarwal is mounting in the NASA clean room. This is a 10K clean room. That means no more than 10 particles per square inch. Very, very sophisticated. He's wearing all kinds of caps and this and that, so that even the air particles will come close to it. This is a picture of me, not younger. With Dr. Von Braun. This is Mr. Heller, who is director of the Space Science Lab. This is during the mission. When the shuttle went up in this space, we are watching on the monitor here. We are all anxiously waiting to make sure that the instrument goes up and works properly. And this is a picture, not a space collective, but this is Dr. one of the Nobel laureate who came here. And this is a picture of me and my wife, Dr. Trollinger, optics expert. This is one of the astronauts who flew in the IML mission. This is Roberta Bondar from Canada. And this is a group of people who I said that the includes one with me, Dr. Trollinger, Dr. Wilcox, Bill Withrow, Roger Cruz, Norman Taggart. He is the longest time of staying in the space station. So an astronaut, he is now at the University of Florida. Research or something there. Ludwig Vandenberg, who flew in the Space Lab 3 mission. He used to work for a company for EG&G in Colita, California, but now he works for another company who works on detector crystals. Mercury iodide crystals for nuclear detection in Florida, near Tampa. This is William Snoddy at NASA, and this is Dr. Stullinger, Ernest Stullinger from NASA, one of them. So I think I'll just skip this. So I think I have tried to convey to you, space experiments are very exciting. Now the next chance of the space experiments will be when NASA builds another vehicle to go to the space station, which will take a long time, I think next 5-6 years. But that will give us also an opportunity. We had an experiment which was approved for the space station, but during last president's regime, the scientific research money was totally cut. And we got a letter from NASA that we going to stop funding you. I was not the PI of the experiment, the PI was Dr. Trollinger. And our aim for that space station experiment was to do more detailed study of the particle motion in space. And we thought it would give us plenty of time when we were in space station. So it was an approved experiment. We were ready to build the flight hardware. Just before that, President Bush at that time cut the budgets to the science and told NASA to go to the moon and Mars. Here we are. But I think the emphasis on science is coming back, because I think they realized, NASA realized that without science, it cannot happen. Just like many years ago, I think in the early 70s, there was an APS meeting held in Chicago, and somebody said in the meeting that we don't have to discover any new thing because we know everything. But he was totally wrong. So many things we don't know is still today.
Any questions? So this crystal is for transfer? And so you are saying that if I try to look with the naked eye, I cannot see the defects? Or can I see them?
On the ground crystal, if you look at it,
Yeah.
you can see the seed crystal there.
Oh.
Because there's always defects near the edges. And always, invariably, you see the seed. Look at a crystal transparent crystal, you see a seed. But in space crystal, you could not see.
Also, you mentioned that you measure what the microgravity levels of 10 to the minus 6 or something.
-6. That's because losing the particle motion.
So, I mean, if you had studied this concentration
Profiles.
profile,
Yeah, we made it
that
actually,
will tell you that?
we tracked the particle. We sort of mark a particle,
Okay.
and then we track the motion of the particle and calculate the fluid velocity. It was pretty sophisticated technique.
How did you identify the 010 phase?
In the TGS crystal, you can identify the phases using X-ray Dawei technique or X-ray diffraction technique.
Using
X-ray diffraction technique
Okay, and what
initially. But now, after working for a few years, we can look at the crystal and we know.
Okay, you can easily recognize. Okay.
The crystal is multifaceted. You can see some of the crystal in the lab when you go down.
Oh, I've grown some.
You have grown some also? Okay.
She's working with Dr. Agarwal.
Oh, Dr. Agarwal, okay. So, otherwise, the other technique is to look at the Dawei patterns. And the Dawei pattern will tell you what phases are, for the Miller indices of the various phases. But now, once work in that, you know, it's just experience.
Yeah.
And it has a cleavage plane.
And yeah, that's a good point. If you take a 010 phase, the cleavage plane of TGS is 010. So if I take a hammer, or I take a one side blade and put parallel to the 010 phase, it just cleaves.
Okay.
That tells us, and the 010 is perpendicular to 010. So that also way you can determine which phase is 001. Once you determine the cleavage, parallel line to perpendicular line to that is the phase is 001.
Okay. Thank you.
If there is no other question, let's thank the speaker. And of course, our next talk will be at 1:15. So you think there's enough time for you to go to lunch and come back?
1:30 sounds better.
You have to be here.
Yeah.
Finishes. Later you start, later you
Okay, then I think we'll start at 1:30.
Is there a time included for nap?
Exactly.
Yes, you can do it.
Have it.
This talk is next, right?
How about you? One long
So I guess
It's Monday. Monday's the hardest day for lectures.
Really? No.
Oh,
Yes.
The other
Low touch.
I cracked everything. I was like, let me make sure.
Because I stopped
Actually, I
just
just
for
realized
that,
that
like,
I
I
got my
So fine. Okay, crystals, do you are they big enough that you see them